So let me introduce you, Alexander Andrianov from St. Petersburg University. Yeah, and you can see the title there. So please start, Sacha. I will tell you when you are left with 5 minutes.
Very good. This talk is based on the actually published paper, published at the end of the year, 2020. And I will show the reference at the very end. And it is done in collaboration with Artyom Starodubtsev and our PhD student, Yasser El-Mahalavi. So, next. We analyze how to quantize 2 plus 1 dimensional general relativity, which actually this quantization has a long story. First, without any masses, point-like masses or cosmological constant, that this theory is trivial, then and this kind of relativity cannot, with the point particles was exactly solved by Gerald Toft. But if model, a model with a cylindrical symmetry is considered, it can be generalized also to 3 plus 1. I will not tell anything about 3 plus 1, but let us find on non-trivialities and subtleties with 2 plus 1. Of course, it was done relatively easy for the cylindrical symmetric matter shell. And in this talk, I present also results for cosmological constant present and existent BTZ Black Hole. What is important, especially our contribution, mostly by Artyom Starodubtsev, it was his proposal. We construct canonical variables which provide a global chart for the reduced phase space of the model. In several papers, the quantization was done only in one, say, quarter or whatever of phase space apart from horizon. And here we use build the global charge. In the case of non-zero cosmological constant and the presence of black hole, we were able to quantize semi-analytically the model in the vicinity of horizon. Pretty far from horizon, the non-commutativity, both coordinates and momenta, I mean, not only between each other, but also inside of this sector, makes the problem pretty difficult. One has to use the full-scale quantum group formalism, which is in progress, by the way. And we, here I will present results around horizon, which is also interesting, because if classically you have a collapse, you collapse matter inside black hole and nothing is going out. But after quantization, there is a penetration back. We will show the probabilities at the end. Okay. So black hole. Mariado Statelbaum Zanelli black hole. We use slightly different notations because it is more convenient in our further equations, but it is like that. In difference, particular in the definition of mass, we use a somewhat different is ADM mass, but does not change very much the result. BTZ black hole is locally is isometric to the anti-de Sitter space ADS2. The variables in SO22 connection we introduce and denote them, and total cross-section consists of the gravity action in the Chern-Simons plus shell action. It is shown here. In order to describe the total phase space, we first, and in a sense, calculate derive equations, dynamical equations. We discretize shell into ensemble of n particles, like here, and go to the limit, of course. Symbolically, it looks as follows. We consider n regions disks, and each disk we have one particle. It is constructed due to Alexeyev-Malkin, and apply the results of Toft-Matschul varying for each particle, then solve constraints, plug the solution back into action, and finally, the symplectic form for the disk collapses looks as follows. The full for cylindric symmetric arrangement of the particle, the sum of the symplectic form for each particle is combined into a single form, this one, where U is a holonomy around the full shell, composed of from holonomies around particles, as shown in the picture. Then, in the neighborhood of horizon, where we can calculate things even analytically or semi-analytically, this shift, in fact, is much less than 1, and symplectic form is simplified to the following action. The holonomy U, it is a role, plays the role of the momentum of the shell. It has two independent components, spatial rotation and boost in radial direction. This is precisely forms ADS2. This is a picture. But you see, it is, if you parameterize it in our way, it provides global charge for entire momentum space. In the vicinity of horizon, principally they don't commute. There is a group characterizing ADS2 geometry, but in the vicinity of horizon, we can simplify. I draw your attention that this is a Penrose diagram, which typically is written in the X space, but we due to our metric, we can write a similar in the
5 minutes left.
Okay, momentum space. And we have, as normally in for Penrose diagram, we have 4 sectors: universe, black hole, white hole, parallel universe. So now let's derive the constraint. U is given by the product of individual loops, and C is given here. Then we, from the condition of trace U is cosine of square root of mass, we derive the Israel equation. And this holonomy can be given a global charge in terms of Euler angles. And this is what we have. In the limit of Q much less than 1, this is what we consider. It is close to the horizon. One of the variable, a chi bar, can be excluded. And finally, we have a single Hamiltonian constraint. Once we have solved, we parameterize wave function by these angles, scalar product, and time is canonical conjugated to rho. But as I showed you, rho is compact, and in rho we have periodicity, and as a result, time is discrete. It has a discrete spectrum. So now we derive an analog of, in a sense, equation, the spectrum of coordinates. This is for positive, for space-like outside of horizon, space-like squared. This is 2 plus 1 dimensional squared or 2 plus 1 dimensional vector. We have continuum spectrum, but separated from 0. And for negative, time like x squared inside of horizon, the spectrum is discrete. And L is a non-negative integer. So, we must not, must be around in the vicinity of horizon, so we cannot say it is exact result, but it is approximate within the vicinity of horizon. Eigenfunctions for discrete spectrum can be easily found from this algebra, actually. They are shown. For continuum spectrum, the wave solution has asymptotic of a plane wave. And we choose linear combination of solution from the condition that there is a balance between incoming and outgoing waves. So quantum version of Hamiltonian constraint is a finite difference equation. It is a Klein-Gordon-like equation for discrete time. So it is a finite difference because time is discrete. So now basically the main result. We calculated these points doesn't mean that the spectrum is discrete. It's simply the numerical calculation with the particular steps in parameters. And here we present two transition amplitudes. One is from inside of black hole to outside. It is a lower line. And the behavior is, after we cross horizon, behavior is exponentially decreasing. Not strict zero, but exponentially decreasing. There is a quantum penetration. And upper line describes the collapse inside of the horizon. It is not exponentially decreasing. But you see, there are no tendency, in principle, there is no tendency to have some singularities. So, conclusions. I hope I am in time. We gave quantum description of BTZ black holes formation due to collapse of a dust shell in near horizon region. The shell radius has continuous spectrum outside the horizon and discrete inside. Transition amplitude between different regions of the Penrose diagram was evaluated, and we discover a possibility for quantum tunneling out of the black hole, which is not possible in the classical limit. Away from the horizon, including central singularity point, which we expect that actually it will not be singularity, but let us first guess, and then when we calculate, we show, of course, we put it into archive. The matter is that momentum non-commutativity cannot be neglected. And we require and apply the full-fledged quantum group technique, which is in progress. These results, the enumerated results, actually admit generalization to 3+1 dimensional gravity. Okay, I stop.
Thank you very much, Sasha. There is a question from Mauro Cambiaso.
Yes, hi, Sasha, nice seeing you. Thank you very much for your talk. My question was, maybe it's very trivial, but was regarding the spectrum, whether or not you can ensure that you have stability, that, so to say, that the spectrum is bounded from below.
You mean spectrum inside, outside, spectrum of what?
When you computed well, when you do this quantization,
spectrum is not. Yeah, here it is just shown spectrum of coordinate square, 2+1 coordinate square. It is calculable explicitly, but of course not far from the horizon. One is simply positive when it is out of the horizon, and inside of the horizon it is discrete and also bounded.
Okay.
This.
Okay, so there is a second question by Rodrigo Olea.
Thank you.
Thank you, Professor, for the nice talk. My question is along the line of stability that Mauro was mentioning. Can you say anything about the cosmic censorship in this context? I mean, because even in the classical context, some people were able to prove that things shall collapse obeys the cosmic censorship.
Well,
I mean, if you try to overspin the BTZ black hole, for instance, would the black hole will resist such a thing?
The black hole will appear, of course, when cosmological constant is non-zero. Black hole arises from the collapse of our cylindrical shell. And the horizon will not disappear. But what is indeed in your question is hidden, that I showed Penrose diagram. Classically, this is our universe, this is black hole. I go inside, but horizon does not allow me to see what is inside, all right? Here, there is a quantum transition. Well, probability is exponentially suppressed, but from black hole, there is a probability to penetrate back to the universe. As to other interesting transitions, like from black hole to parallel universe, white hole, we simply did not calculate yet.
Okay.
Of course, we will calculate. But what we expect that all these anti-horizon, parallel horizon, they are penetrable in quantum case. There is no reason to make a hard wall.
Thank you.